In today's lesson, we're going to be talking about logarithmic functions. Before we can talk about logarithmic functions, we first need to review exponential functions. Exponential functions, if you remember, there's two main categories exponential functions are put into. Either the base, if you recall, this is your base, and this is referred to as your exponent. And for this example here, this would be your base, and this would be your exponent. They're put in two different categories. One is exponential growth, and the other is exponential decay. And that is all determined by the base. So in this case here, a base of 2 would represent an exponential growth, and a base of a half in this example would represent exponential decay. In general, if the value of the base is between 0 and 1, we would have an exponential decay, and if the value of the base is greater than 1, we would have an exponential growth. Let's take a look at a graph of these two exponential growth and decay functions. Okay, taking a look at y equals 2 to the power of x, you can see that as we go from left to right-hand side, our function is increasing. Not only is it increasing, it's increasing by larger and larger values. Every subsequent step that we take along our x-axis, the rate of growth is larger and larger and larger, and that's why it has an exponential look to it. On the other hand, if you take a look at y equals 1/2 to the power of x, as we read this from left to right, the function is decreasing. And that function is now decreasing by less and less values as we move to the right of our function. So in this example here, like we had discussed, this is exponential growth and exponential decay. Now, a quick observation here, notice y equals 1/2 to the x. You could rewrite this using your exponent rules as y equals 2 to the negative x. Therefore, you could view this as a reflection in the line y equals x. So if you take your original function, i.e. y equals 2 to the power of x, and you reflect that in your y-axis, you would then create your exponential decay function, as you see here to the right-hand side. So a quick review here, just wanted to review your exponential 2 to the power of x and 1/2 to the power of x. As you adjust the base, if this base would become a 3 or 5, etc., it would just make the level of exponential growth be that much steeper, or level of exponential decay be that much, sort of decline that much faster. Now, using exponential functions, we can derive our logarithmic function by examining the inverse. Let's take a look at finding the inverse of an exponential function. For this example here, we want to find the inverse of an exponential function. I have our graph here, just a rough sketch of y equals 2 to the power of x. What we want to do here is we want to take a look at the reflection in the line y equals x. When you reflect a function in the line y equals x, that creates the inverse of that function. Now again, when you take the inverse of a function, for every point that you choose, the point directly across, i.e. that point by interchanging your x and y values, becomes the reflected point. That point shares the property that it meets the line y equals x at 90 degrees, and on top of it, it is bisected by the line y equals x. Let's take a couple points on our original function 2 to the x to get an idea as to what this function is actually outputting. Again, this represents the inverse of y equals 2 to the power of x. Reflecting the following 3 points in the line y equals 2 to the power of x, we end up getting 4, 2, 8, 3, and 16, 4. Now, what is the significance of these reflected points? The significance of these reflected points is now what we're going to do is we're going to create a new function. We're going to call that function log, which we will denote as log. We're going to attribute a base to this function. Since we reflected the exponential function y equals 2 to the x, so the base was a 2, we're going to take a look at a log base 2 function. This function is going to take in the number 4, for instance, as our first point we're looking at, and the output is your y value is going to be a 2. Then this logarithmic function, we're going to label that log. We're going to put a subscript to 2 to reference the fact that we're taking the inverse of y equals 2 to the power of x, and now we're going to input an 8, and that's going to output a 3, and you can see here that's outputting a 3. And lastly, let's take a look at log base 2 inputting a 16, outputs a 4. You can see here what this is giving you, what this logarithmic function that we've created gives you, is it gives you the exponent you raise your base to get your input values. So you can see here in this case here, 2 squared equals 4, 2 cubed equals 8, and to the power of 4 equals 16. So when you take the inverse of y equals 2 to the power of x, what you're getting is a new function denoted with logarithm referenced by the base. So if this were to be y equals 3 to the power of x, we would then take the log base 3. If this was y equals 10 to the power of x, we would then take log base 10. But the point being here is it outputs the exponent you raise your base to get the input. So in this case here, log base 2 of 4 is 2, because 2 squared is 4. Log base 2 of 8 is 3, as 2 cubed is 8, and likewise for the last one. Now let's take a look at evaluating the logarithm for various expressions. So for our first one here, we have log base 2 of 4. Again, that's going to output the exponent I raised 2 to get 4, in which case here that is going to equal a 2. And the reason why, as discussed, 2 squared equals 4. Let's take a look at the next example. What do I raise your logarithmic function, again a base of 2, what do I have to raise that base to get a quarter? Well, you'll notice here, if I take 2 to the power of negative 2, that's going to be 1 over 2 squared, which is going to be 1/4. So therefore, the log base 2 of 1/4 is equal to negative 2. Continuing on, here we see log base 2 of 1. So what do you have to raise the base of 2 to give you an output of 1? Well, in this case here, you can see 2 to the power of 0 is 1, and therefore log base 2 of 1 is 0. Let's take a look at some more. So for the following example here, now we've changed the base. This base is 10 now. Okay, so for number 4 here, again, we've changed the base. Now my base is a 10. We have log base 10 going all the way down here. And what we want to do here is, what do we have to raise 10 to get 1,000? Well, 10 cubed is 1,000. Therefore, log base 10 of 1,000 must be 3. In this example here, we have log base 10 of 100. Well, 10 squared is 100, so the output is 2. What do you have to raise the power 10 to get 10? That's going to be 10 to the power of 1. What do you have to raise 10 to get a 1? That's going to be a 0. Now, as we move our decimal place to the left, what do you have to raise 10 to get 0.10? And again, the reason why is 10 to the power of negative 1 is 1 over 10, which is 0.1. Likewise, for our last one here, this is going to be negative 2, and the reason for that is 10 to the negative 2 is 1 over 10 squared, which is 1 over 100, which is 0.01. For the last example here, what do you have to raise a base of 16 to get a 4? Well, you know that 16 to the power of 1/2 is equal to the root of 16 is equal to 4. So therefore, log base 16 of 4 is a half. Let's take a look at going between exponential and logarithmic form. You can see here that the exponential form we've kind of been working with and your logarithmic form are very closely connected here. To answer lots of the logarithmic problems, I'm kind of putting them in exponential form first. So let's go ahead and take a look at how do you go back and forth from exponential and logarithmic forms. In general, if you have an exponential function denoted by y equals b to the power of x, its equivalent logarithmic form will be log base b acting on y equals x. And again, to remind you, the way we got about that is by interchanging the x and y values, you find your inverse of your function, and we define that to be log. So whatever the base b you started off with becomes your logarithmic base. Let's take a look at some examples going between logarithmic form and exponential form and vice versa. So for this first example here, they give us a logarithmic equation. Log base 2 of 32 is 5. That must mean its exponential equivalent would be 2 to the power of 5 is 32. For this one here, we have 10 cubed would equal 1,000. Again, going to exponential form. 3 here, again, I'm in logarithmic form. I want to put this in exponential form. So exponential form would be you take your base, which is a p, raise that to the power of 7, in which case it must be the case that p to the power of 7 is t. And notice how this works is your logarithm base p acting on t gives us the exponent I raised the base of p to get an input value of t. So in this case here, since the output was 7, it must mean that p to the power of 7 equals t. For our next one here, this must equate to being t to the power of x equals m. For the next sequence of questions here, now we're in exponential form. And obviously 6 to the power of 0 is 1. What that means is, what do I have to raise a base of 6 to get 1? That would be 0. And now we're in logarithmic form. Same idea here. My base is 10, so what do I have to raise a base of 10 to get 0.001, in which case that's negative 3. Continuing on here, what do I have to raise 16 to get 2? Well, that's going to be 0.25. And now we're in logarithmic form. And lastly, what do I have to raise a base of m to get p? Well, according to our exponential equation, that must be an exponent of t. Let's take a look at solving some logarithmic equations. So for our first one here, now we've got logarithmic equations. Whenever you're given a logarithmic equation, what you want to do is transform that to exponential form and try to solve it. So in this case here, I'm going to just go right to exponential form for this example. So writing this in exponential form, we know that x squared must equal 25, in which case x must equal plus or minus 5. Now, a couple things to recall here. The value x equals negative 5, that does not exist. And the reason for that is you can't take a negative base on your logarithm. And recall that how we got our logarithmic function was by taking the inverse of our exponential function. Exponential functions only have positive base. So therefore, when you go ahead and calculate the reflection in the line y equals x, it's only for values where the base of your exponential function, y equals b to the power of x, is positive. So because that base was not positive in this example here, this is inadmissible. We cannot consider a base of negative 5. So the only answer, this one, is 5. Let's take a look at the next equation. For the next equation here, same idea. We want to go to exponential form. So therefore, it must be the case that 8 to the power of 1 must equal 2x minus 3. In which case here 11 equals 2x and x equals 11 halves. Or in decimal form, we have 5. Moving along here, we're going to solve this logarithmic equation. Let's go ahead and first put this in exponential form, in which case 10 squared equals x squared plus 21x. And we have 0 equals x squared plus 21x minus 100. Obviously, we have to factor this here. Going through some quick factoring, we can see here that we need to think of two numbers that multiply to be negative 100 and add to be 21. Examining these, we find they are 25 and negative 4. Therefore, this will factor into x plus 25 times x minus 4. So we get two values of x. One is 4, one is negative 25. So notice here I have a value 4 and negative 25. Previously, when we had a negative value, I kicked that out of our answer. The reason for that was that x value in the previous example was in our base. We don't have that here. So it could possibly be the fact that 4 and negative 25 are both admissible values. To take a look here, recall that your logarithmic function looks as follows. For an arbitrary base a, your logarithmic function looks like this. You can see here that the domain of your logarithmic function is going to be all values of x such that x is greater than 0. Right? Notice that your logarithmic function never actually takes in an input of 0. And the reason for that is there's no exponent you can raise any base value to give you an output of 0. So therefore, the domain of your logarithmic function is 0 to infinity. Because of this, we have to ensure that my input value, i.e. x squared plus 21x, for these values of x, 4 minus 25, is greater than 0. So checking this, we get, checking both of these values here, we see that if I input a 4, I get an input of 100, and if I input a minus 25, I also get an input of 100. So both are defined, and therefore both of these answers, 4 and minus 25, are solutions to our logarithmic equation. Continuing on here, let's apply some logarithmic simplification. For this one here, we want to take log base 1/5 acting on 25. So the question becomes is what do you raise 1 over 5 to give you 25? Well, the answer to that is going to be negative 2. And the reason for that is 1/5 to the negative 2 is equal to 5 squared, which is 25. So this will be negative 2. Continuing on here, we have here a composition of functions. Logarithm base 2 acting on logarithm base 2 acting on logarithm base 4 of 256. Well, log base 4 of 256 is the exponent we raise 4 to get 256, and that is equal to 4. So this will be log base 2 acting on log base 2 of 4, and now that's equal to log base 2 of, log base 2 acting on 4 is the exponent we raise 2 to get 4, in which case that's 2, and log base 2 of 2 is 1. So the simplified answer to this logarithmic expression is 1. All right, that concludes today's lesson on logarithmic functions.